Let's talk about continuity. There's three things that must be true in order for a function to be continuous. Those are on the screen in front of you. Limit has to exist. At the same time, the function has to exist. And also, the limit must also equal the function. Well, that's the general gist of it. You're used to just saying, I can draw the entire function or I can draw the entire picture without lifting my pencil off the paper. While that's true, there's a little bit more subtlety and some more nuances to it than that. So let's get into it. Here's the scientific version. First thing is that the limit must exist. So we would say the limit as x approaches some value, call it a, it just generally exists. Also, the function f of a would have to exist at that point. And thirdly, those two have to equal each other. It doesn't matter what they are, they just have to be the same. So given the following function, the question is this function continuous throughout its domain? If I'm asking throughout its domain, you would say no, because clearly there's a gap in here. You're used to just saying, yes, I cannot draw that entire thing without lifting my pencil. But actually what's happening here is the limit is not existing at x equals 2. Therefore, the function is not continuous throughout its domain. If I ask you the question, though, is this function continuous at the point x equals 1? The answer to this question is yes. The limit at x equals 1 does exist. So the limit as x approaches 1 from the left and the limit as x approaches 1 from the right is the same. Therefore, the limit exists, which is roughly at 1/2 to 1/3 on my graph. The function at 1 exists. The f of 1 is 1/2. And the limit being 1/2 and the function being 1/2 both exist at the same point. So yes, all three bullet points check out. I am continuous at x equals 1. You can be continuous at a point, or you can be continuous throughout an entire function, throughout the domain. Throughout the domain on this one, no. At x equals 1, yes. If I went ahead and changed this question, is the function continuous at x equals 2? You can see here, no, it is not. Because the limit from the left of 2 is positive 1. The limit at the right of positive 2 would be 2. And the limit does not exist at x equals 1. So if the limit doesn't exist, then the function is not going to be continuous. Even though on this one, the f of 2 does exist at 1. When discussing continuity, we also must talk about what's happening at the endpoint, because then we're going to start to get into some little trickier situations where we have to make some exceptions. So we would say that a function is continuous at the right endpoint, b in this case, if the limit as we come to x, as x comes to b from the left, if that does exist, and it does. So we are continuous here at b even though it's an endpoint. Now technically we would have to make the discrepancy that the limit must exist at b. And the limit doesn't exist at b because there's no limit from the right. Well, we're going to make an exclusion on this one to that fuller definition because the limit from the left exists, and we'll use that as our value since the function doesn't exist to the right. The same concept would happen if I want to know if a function is continuous at a left endpoint c. In this case, again, I would say, yes, we are continuous at the endpoint, even though the limit doesn't exist as x goes to c from the left. I will kind of, I don't know want to say look the other way, but I will make an exclusion here because the function doesn't exist. So it's a continuous function, even though the function doesn't exist to the left. We have endpoints in this case. So that's going to bring you to continuity on an interval. We would say that that function is continuous on an open interval from a to b. Notice it's parentheses and open, so not including the endpoints. If it's continuous on every point in between. If I switch that on a closed interval, notice the brackets around a and b, including the a and b, two things would have to hold true. The function f would have to be continuous on the open interval, so excluding a and b, and then the limit as x goes to b from the left would have to exist, and the limit as x goes to a from the right would have to exist. For instance, the following picture. The square root function, f of x equals the square root of x. It is continuous. even though the limit as x goes to 0 from the left, I'm coming to x from the left, and I cannot because there's no function over there. Since that doesn't exist, again, I'm making the exclusion saying that this one is continuous on the interval from 0 to infinity. Okay, let's change this function up a little bit. Let me put an open circle at 0, 0 and ask about the continuity of this function now. I would say it is continuous on the open interval from 0 to infinity. However, it is not continuous on the closed interval from 0 to infinity. We're still holding up the first part of the definition with the open interval from 0 to infinity, so we're okay here. But if I include that 0, well, I can't draw the 0 in, or I can't fill the 0 in, so there's no continuity there. There's a hole there, and that's why it's not continuous if I include the 0. But it is if I do include the 0. So in other words, the f of 0 does not exist. Well, if the f of 0 does not exist, but the limit exists, well, now we're breaking the rules, and then again, that's why it's not continuous if the 0 is included in the answer. So if a function is not continuous, we would say that it has discontinuity. And there's several types of discontinuity. The first being a removable discontinuity. In this situation, at x equals some value a, the limit exists. However, you can't evaluate the function. So notation-wise, what we have here in red. So we have the limit existing, but the function does not exist at a. And that can be demonstrated with the following example in orange. If f of x equals x squared minus 9 over x minus 3. And I'm asking you if it's continuous. Well, if you factor the numerator, you would divide out the x minus 3. That tells me whenever factors cancel out that there's a hole there. So the limit as x goes to 3, the location of the hole, f of x does exist. However, f of 3 does not exist because of your divide by 0 error. So you would have to redefine f of 3 by plugging in the 3 into whatever's left over in the function after you've reduced the x minus 3. In this case, it would be 3 plus 3, or equal to 6. So I redefine the function f of 3 to equal 6. That's how we're going to remove a discontinuity. In other words, we're removing the hole, canceling out the x minus 3, and replacing it back with what's left over in the function. There's a point of discontinuity at 3, so plug the 3 into the remaining function. 3 plus 3 is 6. We redefine f of 3 equals 6. A non-removable discontinuity is going to occur when at x equals some value a, the limit doesn't exist. Most often, that's the case of some type of jump discontinuity or infinite discontinuity. For example, if I gave you the function f of x equals 1 over x plus 3, this has an infinite discontinuity. You know that when you graph that, you would take your original 1 over x function and shift it to the left 3. The limit as x goes to negative 3 for the function 1 over x plus 3 does not exist because the limit approaching 3 from the left is negative infinity. The limit approaching 3 from the right is positive infinity. Since those limits don't agree with being the same, we would say the limit does not exist. But what actually happens at negative 3, that's the asymptote. And this has an infinite discontinuity because it goes towards infinity in both directions. You've seen this following function. This has discontinuity. The limits and the functions aren't the same here. We call this jump discontinuity. And here's another example of infinite discontinuity. Y equals 1 over x squared, you'd have the following function in pink. And the limit as x goes to 0, the limit exists because both functions go towards 0 from the left and right of 0. However, there is still a point of discontinuity at x equals 0 because the f of 0 does not exist. You have jump discontinuities, or infinite discontinuities, or what we call removable discontinuities. The removable discontinuity is when the hole is formed, and the way that you remove the hole, again, is to just plug in the remaining function at the point of discontinuity. Let's look at a few example problems here. I can give you the following function for f of x, and ask the question, is this function continuous or not? You should be able to quickly recognize that this one does have a point of discontinuity. You cannot divide by 0, and if you plugged in a -2, that's going to cause a 0 in the denominator. Well, that's going to create a point of discontinuity. Now, whether that's a hole or an asymptote has yet to be determined, but I do know this function is not continuous throughout its domain. If I go ahead and factor the numerator, I would get x plus 2 times x minus 1, and now you can see that these x plus 2's will cancel each other out, and I'm left with the function f of x equals x minus 1. Now you know that the point of discontinuity was a hole at x equals -2. So I can remove that hole by plugging in the -2 into the remaining function in red, f of x equals x minus 1. So the f of -2, -2 minus 1 equals -3. And now I can rewrite the function. To rewrite the function, to make it continuous, in green, I break it into two parts. F of x equals the original function, everywhere except at x equals -2. And then for some value c, I would have to let x equals 2. To find the value of c, to create so that it would be continuous, I already kind of know what c is going to equal, because I've kind of solved that when I did the f of -2. So in this case, that c would be a -3. So I can use the original function, x squared plus x minus 2 over x plus 2, everywhere except -2. And then some value of c, where c is -3, at x equals 2, the point of discontinuity. You'll see a question like this that could be phrased in green and says, find the value of c. Well, we kind of went about that in the reverse process. Similar setup for this problem. F of x equals two parts. Sine 3x over x, everywhere except x cannot equal 0. If you plugged in a 0, you'd have a dividing by 0 error. And then for c, we use the value of c when x equals 0. So I want to find the value of c in this one. So there's no way to factor this sine 3x over x deal, but I do know that there's a hole here, because I can think of this as the limit as x goes to 0. It's the same thing as when I had the limit of sine x over x. I know what this limit is, and I should remember from the flashcards I'm having you memorize that this limit should equal 3. So I'm going to let c equal 3, because this function, if you recall what it looks like, would be the following here in pink, with my hole at 3. So you fill in the hole by finding the limit at the point of discontinuity. So in this case, c equals 3. Another example. F of x in two parts. 3x minus 4 whenever the x values are less than 2, and kx plus 1 whenever the x values are greater than or equal to 2. I want to find the value of this k value here in front of the x so that this function is continuous. So 3x minus 4 is a line, and kx plus 1 is going to be a line. I don't want there to be any type of a gap or a jump between those two functions, so I want to make sure that those functions hit each other. The point of discontinuity would occur where the changeover in the domain is, at 2. So I'm going to evaluate the first function at 2, 3 times 2 minus 4, and at the same time, that's going to have to equal the other function, your kx plus 1, at the value of 2. So I'll go ahead and set kx plus 1 equal to 2 and just simply solve for k. Plugging in a 2 again for the x. Subtract 1, divide by 2, and the k value would have to be 1/2. So in order to make this function continuous, that would have had to have been a 1/2 x plus 1, and then the two functions would overlap each other. And you can see that by graphing both of those functions. Lastly, I want to mention the intermediate value theorem. And here's what that says. Starting out, if f of x is continuous on the closed interval, including a and b, then there has to exist some c value in the subset from a to b, such that the function f of c is between f of a and f of b. In other words, you can't go from -2 to 7 without first passing through the value of 5. Only if the function is continuous. So in other words, here's a function, does whatever. A is somewhere on the left, B is somewhere on the right. And then you have the f of b and the f of a. If the function's continuous, in other words, it's going to contain all the points in between. It's a pretty straightforward theorem if you think about it. You can't go from point A to point B without going through all the points in between, assuming the function is continuous. Taken directly from your flashcards, the intermediate value theorem. You should memorize this one. This would be on the flashcard quiz. This could be the answer on an AP exam. You can say, yes, I know the following because of the IVT, the intermediate value theorem. I would expect you to memorize all the forms and all the closed parentheses versus open parentheses and everything and so forth. That pretty much sums it up for continuity.